I'm one of those civil engineers that were briefly introduced from your experience back in Tokyo. Let's see whether I can really contribute to the outline of that conference. I'm pleased here to contribute to the overall, the aims and objectives of the talk, of the conference. And actually with the picture here, I think all of you have in mind that unprecedented disaster that took place already 13 years back on the 26th of December 2004. That was the large Indian Ocean tsunami. And I'm trying not just to focus on tsunamis, but also to use the early warning system concept, as we've just heard before, to adopt it to other crises as well. And this may be my contribution. Let's move on. Here. Okay, shortly a brief outline. First of all, I was asked to show and tell, that was at least the announcement, that I'm going to introduce you to the typology of early warning systems, its progression and also implementation. Then, of course, I omit, because so many people from the UN world are here, and I don't tell the story about the Hugo framework and the Sendai framework for action we can later on discuss. So that I want to take at the third step, I want to address the core of the conference regarding the fact of the capabilities and limits of early warning. And I'm going to tell you stories about the tsunami early warning from the Indian Ocean. Before I get in my last part, some food for thought, the broader picture of early warning. And finally, I would like to conclude and recommend some points. I think all of you have at least a notion of what is an early warning system. And a brief history of it was not invented, but first mentioned in 1868 by J.D. Cooper after an earthquake struck California. And he had the idea to install a seismic system or an array of detectors that would then transmit a signal via telegraph to the town hall of what you can see here, of San Francisco. It was never installed, of course, but at least the concept was born by that idea. The idea itself developed quite quickly in real-time seismology, especially for post-earthquake emergency responses. And the 1960s and 70s saw the great era of early warning. And of course, in the US and Japan, mainly referring to earthquake notification systems. For example, the bullet train that easily stops by once an earthquake is being detected in Japan, and they stop on land. Or the most recognized Pacific Tsunami Warning Center based in Hawaii after the largest earthquake ever measured or that occurred in the 1960s, a 9.5 earthquake in Chile that produced a tsunami in the whole Pacific and caused devastation and losses even in Japan or on the other side of the Pacific. Similar early warning systems have been installed lately in the Indian Ocean, in the Caribbean, and in the Mediterranean. So the typology of early warning system, to which hazard it might be referred to, could be a general framework. There is an extreme event that suddenly, rapidly emerges and finds an impact lately. And the time it takes is a crisis time, and it's heavily dependent on the onset of the hazard. Whether it's a sudden earthquake, it's a rapid flood or a flash flood, or it's a more creeping process like sea level rise or climate change. So you could adapt that to the early warning system. So you have an array of sensors that could be techniques, right? That could be, devices, but that could also be indicators, as we have just learned beforehand. And you take data from these sensors into mathematical algorithm, and you sort of have algorithms that detect a sort of, say, crisis situation. It then comes, hopefully, to an officer on duty that takes these informations and finally decides whether to issue a warning and disseminate the information towards to the people at risk. And finally, and I posted here in green, you have to deal with the response take that message and do whatever that want. It could be an evacuation, that could be also an adaptation towards the message you are receiving. Finally, of course, the time remaining to the impact should be larger than 0. So these 5 subsystems and the chain of early warning systems finally are also called end-to-end early warning systems. That was introduced by UN ISDR back in 2006. So, 2 types of early warning systems. The earthquake scientists say it's real-time seismology, and you can use data you receive to have other places around or adjacent to that place to warn them about certain issues, enable evacuation, for example, or you could take data from an entity, from a body itself, in order to shut down, for example, lifelines, like gas or electricity or even pipelines, in order not to have further or expanded damages in the structure. The most sophisticated technical early warning systems these days are in Japan, Taiwan, and the USA, so they definitely not the low-income countries, but also in Mexico and Indonesia. We see early warning systems up and running, and even the stipulation of the early warning culture has been introduced, but it's far less developed than the technological part. During the Hugo Framework for Action from the UN World, of course, the promotion and even advancement of multi-hazard early warning system has been promoted, and due to some other agenda processes, and finally in the Sendai Framework, there is, say, from knowledge to action in early warning system, so that we may ask the question, why are we bothering about early warning system? It should work, so we should have no losses at all. The International Council for Science, ICSU, said and raised the question, I think that is very important, why all these advances we experience in the natural and even in the social sciences of hazards and disasters, why do the losses continue to increase? And there is a lesson learned that was advocated by the former Minister for Research and Technology of Indonesia, Kusmanyanto Kadiman, and he gave an interview in the Jakarta Post in 2006, and with the headline that we aim to build structure and culture to respond to tsunamis. What does he mean by structure? Structures and cultures are again the chain of the early warning system. The structure, the technology, what is it about? Sensors, algorithms, detection. Come on. Yes. The decision-making and the dissemination part, and finally the cultural part is the response that we need to address. And here is now, we could also pose a big question mark here, because it has so many dimensions, the responses. The first thing is, do we actually know about the level of exposure and our own vulnerability? Do we receive a warning message, and do we understand the message? Do we then know how to evacuate or to reach safe grounds? And finally, are we capable to evacuate, for example? That is maybe one of the core points, and what it refers to, and that was being described in literature by Shah from Caltech, as far as I remember, is the phenomenon of the last mile. And it says the dimension of the response is pretty much dependent on the preparedness, the perception, understanding of a warning, and finally the capability of it. So, the issue, what Shah is raising in his document, say the issue could be whether we are reaching people who represent the last mile on this early warning pathway. And there was a couple of earthquakes back in the late, 2007 and 2009, and Science and even Nature, they argued, yes, we are still, the preparedness is being improving, and of course, decentralized local initiatives are needed. And Schiermeier from Nature said, after 5 years, the technology is in place, the local preparedness is less advanced. So the cultural part, again, is missing. And even as we speak today, this is maybe the largest investment we have to take care for, so that community-based public education and evacuation drills are essential. What is the end-to-end system. That was back in 2006 from the Intergovernmental Oceanographic Commission from UNESCO. They said, we are having a, oops, no, go back. We have a couple of sensors in the ocean, or I'd say floating on the ocean, gaining information about the hazard, the earthquake that triggered a tsunami that is then being transferred in real time via satellite to an office, whether that is in Delhi or that is in Bangkok or that is in Jakarta. And from there are officers on duty who can deal with this sort of information in order to disseminate or to make a warning message finally. The German contribution, you all heard about that, well, the Germans in-house saying we invested up to 60 million euros in between 2005 to 2012 to deliver the German contribution to the Indian Ocean tsunami warning system. And I don't go into detail here, that is the technological part of it, but we also had in mind from the very beginning to have the capacity building component on top of that. That means not just training of academics and scientists, but also of governmental bodies and of course of communities itself. So that is essentially inside an early warning system. A story from Padang in Indonesia, maybe quite, well, stunning information. That is the city of Padang, that is just in Western Sumatra in Indonesia, is one of those cities that is at highest risk due to the simple fact it's seismically locked. Seismic energy has not been released since more than 200 years already. And the area there is an urban agglomeration of almost 850,000 inhabitants, low-lying coastal region. They experienced definitely earthquakes, severe earthquakes, and larger tsunamis back in the 18th centuries, but also in the 19th centuries. And the likelihood, or the likelihood of a major earthquake is still dormant in the area. An 8.5 up to 9 earthquake is waiting to be released in the days and the years to come. So we actually see that the catastrophe will happen there. And this is where we said we will jump in and try to deliver some more knowledge and training aspect in the city of Padang. When we started that project, in 2007, there was neither a tsunami hazard map nor any evacuation information for that city. So Hannes Taubenberg and other colleagues, we did use classification of land use and land cover. We had debates about to use digital surface model or digital elevation models so that we could distinguish in between the land cover. We even had the physical urban structure analysis, whether that are concrete houses, wooden houses, so depending on the susceptibility of these structures. And we could even, in combination with household surveys, gain information about how many people are staying in what location, in what area, because this heavily depends on evacuation planning, whether it comes in the night or during rush hour or even Friday morning in a Muslim country. So this is what we considered. As a coastal engineer, of course, I deal with processes on the coasts and describing and dealing with the inundation dynamics of waves that can enter the countryside. And here you see one of the products we finally presented. Yet this is a plausible numerical and physical sound representation of the tsunami that might occur. It's not, the full, there is some probabilistic behind, this is what we have to say, and it's in interaction with built infrastructure. What you can determine right now is also that even the rivers are quite heavily exposed to the tsunami because it penetrates and funnels into the land. And we could then, of course, derive on a very precise level, streetwise level, how far the inundated area will be flooded. We furnished, of course, the authorities and trained them in a geographical information system with all data we acquired by that time. And we were capable of identify hotspots of vulnerability in the city of Padang. That means identification of main activities and mobility. well, I don't go into detail here, but spatial distribution of demographic groups, gender, age, education, income and poverty status, just what Hannes Taubenberg presented before, and even critical infrastructures that can be used for decentralized capacities of evacuation, for example. And of course, we had also knowledge about the working place and in settlement areas. All data were handed over to the authorities of Padang. A quite depressing analysis we also conducted here was with the colleagues of Technical University of Berlin, and they did do an evacuation analysis for the city of Padang, and it relies on a rational and well-trained population, and it says it's an evacuation with pedestrians at only, so no cars, no bicycles whatsoever, and it's a well-trained population. In case of an earthquake, everybody knows what to do. And the result says, reaching a safe zone that is approximately that gray line here, far more inland, it says how much time it will take for you to reach a safe ground. And with the knowledge that the lead time between an earthquake and a tsunami is about 25 to 30 minutes, until the waves reach the shore, you can easily imagine that 250,000 citizens are endangered, exposed, and roughly 100,000 citizens even won't make it in time, although they are well trained. So that left room for recommendations and some pictures here from all these workshops we took in the area. And finally, the official Padang map was launched, and we were really glad to see that happen, because it was, of course, endorsed by the Lord Mayor, and the tsunami inundation, but also the evacuation map was up and running ever since. And as we know, although our project terminated by that time, they are even doing evacuation shelter building and so on. I'm running out of time, but this picture should give you an idea about the continuation of training activities from the community itself. That was being conducted by GIZ and colleagues to train once in a while, at least once a year, to train on a district-wise level where to leave or what to evacuate to. So that the broader picture I wanted to share with you, but I'm already running out of time. I just wanted to see whether these Jakarta example here, is this an episodic phenomena, or is it even the new norm of inundation and coastal flooding in an urban city? And even the small island development countries are suffering, not just due to sea level rise, but due to phenomena that are triggered by incremental sea level rise. That is called a low-frequency resonance on fringing coastal reefs or coral reefs. And we are doing a project in the Maldives where we observed these phenomena already. And that leads not to salinization of the islands in due time, not just in 50 years from now. It happens right now. And so what it is all about, I'm not going into that one here, so I'm skipping it. Come on. Yes. So the broader picture about sea level rise and subsidence, I wanted to bring in the dilemma of sinking and drowning cities. So the dual forces that are coming into the game. And finally, I wanted to say, and this is now my picture here, we already know in so many instances, we do not need even to detect or have new indicators. We already know about the processes going on. So the time is diminished to react to that. And even the responses in the creeping phenomena or the creeping processes, we need to find adaptation answers or adaptation processes. So the translating the scientific evidence to the progressing decision making, and finally, really to stimulate community-based action, so that I conclude that early warning systems itself have capabilities and are proven for sudden and rapid onset crisis, like earthquake, tsunamis, and flash floods. They are less developed and even not standardized for other hazards, like, say, landslides or droughts, famine, or effects of sea level rise. So further research, definitely. on the 5 subsystems we've just learned about. And we need to reach the people living or representing the last mile. This is what the talk is about. And finally, of course, and maybe that is in line what Jacob just made as an experience in Tokyo, we need further to promote and enhance early warning system. And through transdisciplinary approaches, as this conference, also international cooperation, and a strong need for standardization that I would like to take care for. And of course, and I think that is the heart and the core also of that workshop, the capacity building programs that needs to be established and progressed, not just for evacuation drills, I showed you the pictures, but also for educational efforts and training activities. And with this having said, a last slide from, well, my literature and from the Maldives, where these severe erosion take place already due to the low frequency resonances on the coastal reefs. Thank you very much.